This conference is about virtualization, and Srinidhi asked me to talk about network virtualization. So that's what I'm going to talk about, and then how does it relate to software-defined networking. And some of these things are very new, like last year and year before. There are 4 parts to my talk. There is no sound here. There are 4 parts to my talk. Huh? There is no sound here. Okay, good, thank you. It was virtual maybe, now we have a real sound. So, I have 4 parts. First is virtualization, how and why. Then some of the recent things that the networking people have done for virtualization. Then go to our own research project. I have to talk about my work as well. And then software-defined networking that is taking over the world. So first of all, we all are living virtual life. This morning you saw how you can skydive from your room, right? And today we talked about, in the morning speaker talked about shopping. So actually it turns out virtual is better than real, believe it or not. Alright? Virtual shopping people are making more money than the real ones. And this conference is on virtualization, but 2 years from now this will be a virtual conference. And you will save a lot of money because you don't have to come here at all, right? And I'll do virtually speaking from wherever I am. And education is becoming virtual. You don't have to go to the courses. The people in United States can teach people in any other country and so on. And everything else, right? I know what you're looking for, but I'm not going to talk about that. Right? So, with that, let's move on and talk about why do we do virtualization. First of all, because the resources we want to share, the computers have become too fast, the networks have become too fast, and it's not good for one person to have all that resource. And it's not economic to have all that resource, and therefore, we want to divide this into pieces, and so that is one reason. Second thing is, sometimes even if we want to share, but the thing is, even if we really want to isolate, so we want to put a wall so that the people who are on the same network, on the same computer, cannot see what I am doing. Right? So we need to virtualize the network for that reason. Aggregate. Sometimes the resources are not enough. And we want to make a big resource out of little ones. Like virtual memory. Right? Then we need to virtualize it. And we will talk about how we are doing in networking that as well. Dynamics. Sometimes with the virtual, the good thing is that you can change things around very fast, which you could not do with the physical things. Right? And so fast allocation, changes of the size, scalability in general is much easier if you virtualize the resource. Ease of management. It's much easier to manage some things which are virtual than things which are real. And things are moving, and again, that requires virtualization. So, the question is, what is happening in virtualization? Obviously, there is a lot happening in the storage area, first of all. And I put storage first because I did my PhD in 1978. I should not be giving the dates anymore, but in 1978. And that was on virtual memory. Paging used to be our hot topic at that time. Right? So virtual memory was the first one, and now then we have layer 1, L1, L2, L3, I don't know how many L caches. Right? And then we had virtual disk, RAID, and then cloud storage now, S3. Computing. The first thing what we got was virtual desktop, and we call it thin client, and that was better. As you can see, that thin client is much better to manage, much easier to handle than a thick client, the real desktop. We moved on from there to virtual server, and we started putting virtual machines on a computer, and now today we have a cloud, which is a virtual data center. So you don't need a real data center, you have a cloud. Well, networking. It turns out networking is plumbing. in the sense that nobody is selling virtual. There are companies that are selling you virtual storage. Amazon sells S3 and other companies, I can name it. People are selling virtual computing, everybody, including Microsoft and Google and so on and so forth. Nobody is selling virtual networking because networking is plumbing. The thing is, plumbing is something that you don't really sell, but you cannot build a house without plumbing. Right? So without networking, none of this would have been possible. And without networking, none of this is possible, and therefore most of the fundamental advances that are required today to make cloud computing possible are in networking. And I will give you a very small, what I call tip of the iceberg presentation in the next few slides. So all the stuff, first of all, all the stuff. So in the networking we had virtual channels in the old X25 days, where you didn't need a real wire, you had a virtual channel, which meant that you could take a piece of the wire and you could share a wire among hundreds of people. Then we had virtual LANs to isolate so that your department cannot see my department's traffic. Then we had virtual private network, similarly to isolate my traffic on the internet. But today, the network consists of many things. A host connected to a L2 link. I hope everybody understands what is L2. Okay, so for those of you who are not networking types, L2 is layer 2. We have 7 layers of ISO, and layer 2 is Ethernet, and so we call it L2. Layer 3 is IP, we call it L3. TCP is layer 4, L4, and so on and so forth. So we have L2 link, Ethernet link connecting to L2 bridges, connecting to L2 networks, and then L3 links, which is the IP links connecting to L3 routers, to L3 networks, to L4 transports, to L5 applications. Applications are layer 5. Alright. Now each of these can be and need to be virtualized. So we have virtual host, virtual L2 links, virtual bridges, virtual routers, virtual networks, virtual applications, everything is virtualized. And a new technology is required for each of those things to be done. And so I'm going to give you a tip of the iceberg of what is being done. So first of all, let's start with a NIC. What is a NIC? A NIC is the network interface card. Every computer that you buy has an Ethernet card in it. That's a NIC. It might have a 802.11 wireless card in it. That's a NIC. Network interface card. However, when you put 10 virtual machines on a single computer, you need 10 NICs. Are you going to put physical NICs? No. Obviously, we need virtual NICs. And there is a competition in the industry as to who will do it. So first of all, I'm going to talk about it in a minute, but basically, so the idea is that for each virtual machine you need a virtual NIC. And I'm going to use this terminology, V for virtual, P for physical. So there is one physical machine on which we have N virtual machines, and each virtual machine has a virtual NIC, and inside the machine we also need a switch to connect all of these. Alright? And then that connects to a real NIC, physical NIC, PNIC. Right? And that connects to a switch which is a physical switch. Alright? So the question is, so the notation is P for physical, V for virtual, N for machine. Generally the dotted things are virtual, the solid things are physical. So what is the solution just for virtual NICs? There are many standards being developed in the last few years. So first of all, VM vendors, the virtual machine vendors, VMware and so on, they said we have the solution, and their solution is to put software inside their hypervisor, the operating system that runs underneath your Windows or your Linux or whatever to support these virtual machines. And in that one, they put software virtual NICs and the virtual switch. Well, the networking vendor found that not really acceptable, so they have their own solution. They said this is too much overhead on our machines, and that it is not easily manageable from outside, and that it does not provide all the nice features that we need in a NIC. So they came up with the NIC vendors. NIC vendors are Intel and other companies that make those chips for the network interface card. So they came up with a solution which is basically called SRIOV, and that means that That means that they used a technology on PCI bus, so that on one single PCI bus they can create virtual ports. So you have virtual NICs, multiple virtual NICs. So you have one physical NIC on which you can create as many virtual NICs as you want. And because this is all being done in the hardware as opposed to being done in the software in your CPU, this according to them is much better. Alright, then comes Cisco's and the other networking companies, Juniper's. They said, no, this is not good enough, we have a better solution. So they have this third solution where they say switch will provide all this virtualization that you need with little help from the software, and that solution is called by the IEEE 802.1 QVG standard and 802.1 QBH standard. They're not done yet, but they're being done. And these, according to these standards, then you will be able to set up many virtual channels through an external switch, and that the advantage of that approach is that this external switch is easily manageable from outside, and it has all the features that the networking guys have developed over the last 20 years. Any of the things that you need from networking is there in that physical switch, and therefore this is according to them is the best solution. So I am not going to take a side here, but basically, as you can see, that there is a lot of money in virtualization, and every part of the industry says that let me get the piece of the pie. Then we move on. So this was just the NIC. Now what are happening in the bridges, L2 bridges? Well, in a data center you have lots of bridges. You have a rack switch, which is a bridge, rack switch, a bridge on the top of every rack. Then you have the other switches which connect those switches, and then other switches which connect those switches. And so the question is that you really have to find the routes and this and that. It's all too complicated. So they said, why don't we create a virtual bridge that looks like a 1,000-port bridge, but actually it consists of 48-port bridges connected together. So far you are concerned in managing those things, you just think that everything is connected to everything else, and the bridging people will take care of all the details. So that standard is called 802.1 BR. Alright, it's called bridge port extension. Moving on, what are the issues if you want to put multiple virtual machines on the same computer belonging to different companies? So you have the virtual machine which is being used by, and let's take a competition, let's say Wipro, and the next to it is running another virtual machine which is used by Infosys. Would they like to share the same LAN? Obviously not. So now we need to separate them out on the LAN. We need to have multiple virtual LANs on each of those virtual machines, in those physical machines. So here in this picture I have shown you 4 VLANs, a blue one, a yellow one, a red one, and so on. And so we need a technology that can handle this complication. And that is called, and there are again, right now there are multiple proposals. The first proposal which came from VMware is called VXLAN. By the time it went to IETF, it is called NVGRE, STT, and there is a whole new group called NVO3, Network Virtualization over L3 in IETF going on. Alright? Now we move on to virtualize the data center. Data center is basically consists of virtual machines running. However, it is quite possible that there is not enough, let's say, resources in one data center, and then you want to combine 2 buildings which are across the campus. So one building here and one building maybe 10 miles from here. Can they become one data center? We said that we need to virtualize whenever we have something small and we want to make it one big one. Why we want to make it one big one? Because it is very difficult to move from IP domain to IP domain. It is very easy to move on Ethernet. So we want the whole thing to look like one Ethernet, not 2 Ethernets. Because if you want to go from one IP domain to other IP domain, your subnet changes and things just become very slow. Alright? So to connect this whole thing as one data center, this dotted line, there is another standard called TRIL. Trail is transparent interconnection of lots of links. Alright, and there were competing proprietary standards just before this, but the Trail is now the standard, so this is, and it's set, so now that is, I'm not going to talk about the other previous ones. That is all I'm going to say about virtualization in networking, but I want to bring it now, the next part of my talk, which is basically about what we are doing, our research. And there are two dates I want to bring to you. First is August 25, 2006. That's the birth date of cloud computing. And let me tell you why. And this is how it happened really. A friend of mine told me this story. He works for Amazon obviously, so there might be a little bias. But here is what happened. Once the Amazon CEO visited the data center and said, so many computers, are we really using them? So the people said, well, sometimes we do. So how often? They said 10% of the time. So what do we do 90% of the time? We have to just wait for those 10% of the time, right? Because the utilization is so low. So he said, why don't we rent them out? All right? And Amazon had done this before in their shipping business. They were shipping their own books first, but then they said, anybody's book we can ship. You just send it to us and we will ship it to the customer. So they said, why don't we do the same thing in computing? And he gave a challenge that you just figure out a way for us to be able to rent computers. And believe it or not, 2 years from then, few years of then they announced EC2, elastic computing. And this invention didn't come from Google, it didn't come from Microsoft, it did not come from Apple, it came from Amazon, a book dealer. Right? And it turns out, while we think of Amazon as a book dealer, but their fastest growing business is web services. Fastest growing, not the most money making right now. But if you look at the slope of the curve, their fastest growing business is web services. Forbes, just last few months ago, said that this is what is going to drive Amazon in future. Then the second date, June 29, 2007. That's the birth of, I could say mobile computing, we could say smartphones, or we could say anything, but that's really when we really started using internet from the mobile internet basically. Because iPhone was announced on that day. I have had a smartphone for years before that. I had everything that was ever announced, but we really didn't do any networking on that on the road. But the day we got the iPhone, then the world changed. The world changed for everybody, not only for the user, but as well for the suppliers. And so that is the date when the mobile internet was born. And almost all the services now are mobile apps. So if you are running a school, if you are running a bank, if you are running a hospital, you have to have a mobile app. Because without that, you are not doing your job. Right? And all the services, including Google, Facebook, Bank of America, they all are mobile apps, and all the services need to be global. And that's another thing, the world has become flat. Right? And so if you develop a small game, such as killing the bird, I forget the name, what is it? Angry Bird, right? You have to be angry globally, right? So the thing is, you have to do globally. It means you have to deploy globally, and the only way to do that is to rent computers globally, and which you can do very easily. Right? Renting a computer is not very difficult because there are data centers in India, there are clouds in China, there are clouds in Europe, there are clouds in US, of course. But the problem is networking them. So what we need is, we already virtualized the data center, but now we need to virtualize the internet, the whole global network, so that you can get a piece of your network and he can get a piece of their network, virtual network, so that you really don't need any real resources, just the virtual resources. And that's the technology I want to talk about. So let's talk about how the virtual services start. So every service that I know of, whether it is Google or whether it is Facebook, they start from university campus with a single computer, to see if this will work. And if it works, they go to California, they move to Silicon Valley, rent a data center, and actually not rent, in those days you could not rent, so it set up a data center, and if you succeed, then you move on. But let me see first, let me stop right here. When you set up a data center, then you need lots of other stuff. You need load balancers, because now you have tons of servers, you need SSL offloaders, you need firewalls, and I could go on. Lots of devices that we call middle boxes, are actually the right term is application delivery controllers. So these are required for application delivery. And then you move on to the world. Once you become successful in Silicon Valley, then you move on to the world, and then you rent a cloud in China, Asia, and India, and everywhere place. And now the question is, where is your middle box? Where is your load balancer? Where is your whatever you need fault tolerant server? So that's the problem we took on to solve ourselves. Actually, Google has already solved this problem. Google is already worldwide, and the way they solve it is that in every ISP, what is ISP? ISP is the Internet Service Provider. In every ISP's office, which are called POPs, point of presence, in every POP they put a box called Google Box. So when you connect, if your traffic is going to Google, it is given to the Google Box, and Google then takes over, because they have very high speed links connecting those Google Boxes, and the ISP is very happy with this arrangement, and it gives it free to Google, because most of the traffic is going to Google, and the ISP is very happy that it is not going to need to be given to their provider. Every ISP has their own providers. If they gave it to their tier 2 providers, it will cost them money, and the other giving it to Google right there is free. So it's good for Google, good for the ISP. But there are two problems. I and you and the Angry Bird generator or application writer cannot use this arrangement because we don't have Google dollars. Right? We can't go to every ISP, and we cannot even have the high-speed links, and we cannot have so many boxes. So our solution is to do the same thing virtually, so that we set up one network which can be used by everybody else. Obviously Google is probably not interested, but everybody else can use it. So what will happen is, these are the boxes. Everything that is red is our new thing, everything that is blue is the old stuff. So most of it is actually old, only few boxes are red, including the servers and the clients. And then if we use this technology that we are developing, which we call Open ADN, Open Application Delivery Networking Platform, it will basically allow the box to know exactly which ASP, Application Service Provider, this is for. So the Bank of America is an ASP, the Angry Bird is an ASP, Facebook is an ASP. Which ASP it is for, where their servers are, where is the right place to send it, and depending upon the message, whether it is a video message, it has to go here. If it is an accounting message, it has to go to Silicon Valley, and so on and so forth. All that can be done, and the challenge is to do it without letting the ISP look at the data, because hospitals would not want a packet, the ISP, AT&T or Airtel, to look at the packet inside and see, well, this is a video message, right? Because then it will be a violation of privacy. So the idea is, how do you do this without with the data being totally encrypted? So obviously the solution is what we call cross-layer communication, is that we have something in the header which says this is message type 5, and what is type 5 the ISP doesn't know, but ISP has been told, whenever you see my message type 5, please send it, handle it like this. So that's the whole technology. So with that, we are able to basically virtualize the internet, in the sense that you could put your middle boxes anywhere, you could put your servers at as many clouds as you want, and your traffic will go exactly as you want, as you programmed. Alright, now there are two things that help us, two new developments in the technology which happened in the last 2 years that I need to talk about. and one of them is centralization of control plane, called open flow. So what is centralization control? First of all, the current thinking, first we need to decouple the control plane from the data plane. What is the data plane? What is control plane? Well, when you send a message from here to there, we need to prepare a routing table to figure out that to send it there, I have to send it here, from there to there to there, right? And that preparation of the routing table is control. And then when so there are lots of routing messages which are sent, those are control messages. And then there is a data messages, so when I send my packet is a data, and that packet goes, and if there is no control, the data will not get there, right? So we need control plane, and the question, so far, and the original thinking in the internet design was that everything has to be distributed. Remember why internet was developed in the first place? Because the United States was afraid that Russia will bomb AT&T headquarters and we will be all done in terms of communication, because AT&T headquarters was the central point of failure, right? So that's why the DARPA, the Defense Advanced Research Project Agency, funded development of the internet so that we have totally distributed system such that you could destroy as many routers you want, the system will continue. Now the thinking has changed. 40 years, 2 generations later, 20 years is a generation, right? 2 generations later, we are thinking that that is not the right way. Centralization of control plane probably is better. While data plane can be distributed and the data control plane can also be distributed, but centralization has its advantages and it is very easy to manage, it is very consistent, and so on and so forth. So believe it or not, today's thinking in the networking community is centralize the things. So we are just going back in the whole 360 degree, right? In that one. And it really turns out that centralization is better. You think about your organization. If your organization was totally distributed, right? Will it work? If everybody was equally responsible for everything, it will not work. So what we do in our organizations is we put a boss which has a little bit more power, and then bosses under bosses under bosses. So that's how the organizations work. So why not our control plane? And that's the thing we are thinking right now. Alright, and this is success. By the way, it would be very difficult for people who have not heard of this before to take this, but today every company, whether it is Cisco or Juniper or something, has bought this, and there is a group called Open Networking Forum where every networking company is a part of, and there is a lot of development going on. Billions of dollars being exchanged. A company called Mesera was bought for $1.26 billion a few months ago with few employees simply because they were the originators of this idea. Alright, second development that is happening is what we call software defined networking, and that is the standardized abstractions. What is standardized abstraction? So basically, let me go back, before I go to the standardized routers, let's go back to standardized computing. The reason personal computing succeeded is because there is a standard for everything. But for networking there is no standard. For example, every router from different company has a different software, different hardware, and different interfaces. You cannot really use Juniper's management plane, their management, for Cisco's routers. You cannot use Juniper's box in a Cisco router. Right? There is no standardization. So the idea is that we really need to standardize these internal interfaces such that you could take anything from anybody and put it together. And that's what we did to computing when we moved off in 1981, when we moved off from IBM 360 to IBM PC. With IBM PC, you could buy the chip from any vendor, you could buy the operating system from any vendor, and you could buy the application from any vendor, but there is a very well-defined interface and you could put it together. That brought the cost down from $1 million to now a few $100s. We need to do the same thing for, and then finally in 1998 we brought it down even further by virtual machines and having a standard. We need to do the same thing for networking. And so now there is an effort going on to define these interfaces, and basically, so there are many layers. Now we don't want to call them layers, these are called abstractions because we already have 5 layers. We talked about L1, L2, L3, L5. So the abstractions, so there is a virtualization layer, then there is an operating system. So there are people who are writing network operating systems, and then Nisera was one of the companies that actually did some of that. And then on the top of that you write applications, and then on the top of that you write more applications. The hardware itself is somewhat standard. So you could buy, the key point is that with this thing happening, you could buy anything from anywhere. You could buy the hardware from one vendor, you could buy this virtualization software from somebody else, you could buy the operating system from somebody else, and so on and so forth. And since there is a lot of competition, there is a lot of price drop. Now, is the industry taking it? You bet. Cisco has invested $100 million in a startup, its own startup, which they will buy it back for $800 million. And obviously they are doing their own internal development. And every other company has invested upwards of $100 million to get this thing done. All of this happened in the last 2 years. And so this is what we call SDN. I could go a lot more, but I'm not going to go to more. Basically, it has 2 interfaces, a southbound, which is from this software, how do you control the hardware, and that is called open flow, and a northbound, which is how do you use this thing to write your own applications. So we are using that northbound. So OpenADN is an application on the top of software-defined networking, and so that helps us a lot. Every vendor, as I said, Juniper, Pronto, Netgear, HP, everybody has their open flow switches. All right, and so there is a lot of development in southbound. Northbound has not started yet. Northbound is still with us, people like us, research people. So what is the impact of SDN? Well, there is a lot of interest in the industry. Why? The reason is because if the prices of the switches goes down, if the prices of the router goes down, who is going to benefit? Google. They buy thousands of routers every year. AT&T. They buy thousands of routers every year. And you name your own favorite ISP, they are going to benefit. So anybody who buys a router is going to benefit, and therefore they are saying, even though people like Cisco and Juniper will not want to see this happen, but they have to give in because that is what the customer wants, right? And they have given up. So basically, with this, the prices of the networking equipment is going to come down very significantly, and that's why every company is interested in this. So there is a tsunami of software. Now, while the software-defined networking was just done 2 years, and now everybody else who has anything to do with the networking in any other field, now everything they are saying will be software defined. There is a whole tsunami coming in. The whole hardware will sweep away. Why? Because today you don't need, today the hardware has become so fast. You have 16 core and 4 cores and so on and so forth CPUs that are so powerful that you don't need any specialized hardware to do routing. You can do that in the software on a standard processor which is very cheap. Right? So people are saying, why do we need this special hardware for anything else as well? So you want to design a base station, we will have a software-defined base station. You want to write a IS, whatever the gateway, SG, SN, and I forget all these names. All these cellular companies have all these kinds of gateways. They are saying they are going to do everything in software. For hardware, we got Intel, period, done. A standard processor. So even though it has nothing to do with those abstraction layers, but every company doing anything to do with computing, whatever it is going for a software-defined that thing. So I heard presentations about software-defined optical switches. So previously you need to have very special hardware to switch your wavelength from here to there. They said will have software-defined everything. And so there is a wave. When there is a wave, we call it, like basically this is like wedding. Before marriage, the life is made up of dreams. there is this person who has all the right qualities that we want in the world, and my life will change. But right after the wedding, well, the life is not that good. I mean, there is some deficiencies in this person, and we all learn to live with that. But that's what happens with new technologies. So right now, this year, we are in the pre-wedding phase with the software-defined stuff. And maybe at some point, we may not be in the same phase, but my message is that if you are doing anything to do with the computing or networking, you have to be in it before the wave. You have to be in it now. If you are doing any research in networking, if you are doing research in computing, you have to be in before the wave, because you cannot make any money after disillusionment. You make the money here, not there. Whether you are a researcher, whether you are a company, whether you are a Wipro, or whether you are in Infosys, you make money here, not there. All right? And so this is where SDN is, and this is the thing that's why we need to know about it. I already covered that one, so I'm going to move on to the next one, and that is that one of the, now I'm back to just one more slide on my research, OpenADN. So I have been in the industry and I have been in the university, if you know, 16 years in the industry, 5 years of my own companies, of 20 years, 21 years in the industry, 10 years in the academics. So basically, when I was in the industry, my boss taught me some things, saying that, you know, if you develop something new, you have to follow certain things so that it will succeed. And so those are the things that are on this slide. First of all, we are not changing the internet. We don't expect that one day people will just start using OpenADN routers. No. And that is the problem with many of the technologies that have been developed so far, even in IP, some versions of IP, that expected that one day the whole world will change to that version. And that's not happening very easily. Right? So we are assuming that the whole thing will be current as it is. Only some boxes on the edge will change, and we are designing the boxes such that they coexist, so the old traffic can go to the new box, the new traffic can go to the old box, which is difficult, but that's what we are doing. So our traffic can go through the IP routers, except that when you mix up the two, you won't get the benefit. All right? Anything that goes new, but well, I mean, it will go to the old one also, but basically anyone that uses the new part will benefit. And so incremental deployment, you can start with 3 boxes. Economic incentives for the first adopters, whoever buys the first box also benefits. It's not that they have to wait for 1,500 other people to buy the same router. And the resource owners keep complete control over their resources. So there have been other previous attempts to make the router software programmable, but they failed because, for example, there was active networks in 1990s, and there you could put a Java program in your packet, and it will be executed by the router to see what to do with this packet. Well, which ISP will like that to execute the Java program? None. Right? Everybody wants to have complete control over their resources. So same way here, we have designed such that you do not change the routers to the ISP. ISP has complete control over what gets executed, how it is done, how the packet is sent, how the packet is handled. You just tell the ISP, this is what I want. Just like you tell that I want the packet to go from A to B, ISP decides how it gets from A to B. All right? And so, good example is Ethernet, which has followed these principles. And by the way, I was involved in the first Ethernet 1 standard. That is when the life started in networking, 1978. And so, Ethernet until today, when you buy a gigabit Ethernet or 10 gigabit Ethernet, you don't even know what is on the ground, and it all works. But when you buy something else in IP, it doesn't. All right. That brings me to the end of my talk, and there are 3 key messages. First message is that because of the cloud computing, to make cloud computing successful, we need to virtualize. We need to virtualize the computing, we need to virtualize the storage, but most importantly, we need to virtualize networking. So there are lots of research issues there, and there are numerous recent standards are on the network virtualization. Second message is that there are two fundamental shifts in the networking design in the last 2 years. Two fundamental shifts. First is centralization of the control plane. I didn't say much enough here, but everywhere it is taking over like a wave. All the ISPs are saying we are going to centralize our control, we are going to centralize our control, same way they are saying we are going to software define everything else. It's coming in a big way. So two of those changes, centralization control plane and then standardization of networking abstractions to bring it software defined networking. And not only software defined networking abstractions, everything else is becoming software defined. Now it has become a kind of a, anything you design, you say, well, I'm developing software defined this. Regardless of what you are doing, you could be doing an optical switch, you could be doing, as I said, you could be doing anything. If it is software defined, that is the new thing. And then we are also saying the same thing. We are software defined internet multi-data centers stuff. So you could define in the software what you want to do with your application, and the internet will do it. All right? With that, thank you.
Thank you, Professor. As we're running short of time, we will not have any questions now. Professor Jain will be available during and after lunch. So you will please have your questions posted and we will answer after lunch. Thank you, Professor.
Just want to add a comment. You said, Ethernet follows all the principles, and IP did not. The said here is Ethernet is IPv6.
I will tell you what is the difference. The basic reason is IP version 6 was designed by academics. Believe it or not, the guy was actually a Stanford student, not even a PhD completed. All right, IPv6. And the day it came out, I was working in Digital Equipment Corporation, and my boss, Tony Rock, who I respect a lot, basically said that this is not compatible. You have to design an extension so that it extends, not replaces. There is no transition strategy. The students could not think about transition strategies, but in the companies we did, right? So there was no transition strategy, and that's why it has taken 20 years. We have been teaching IPv6 since 20 years, but it is not there. It is there, but it is not there. My PC has IPv6, but I don't use it. Why? Because you don't use it. All right? Okay, all right. So, good lunch.